very good morning to all of you. We start with our discussion on dynamics of viscous flows. Yesterday we were discussing about dynamics of inviscid flows, that is cases where viscous effects are not important. Today we will be discussing about first some basic governing equations that describe viscous flows in contrast to the inviscid flows that we discussed yesterday. The inviscid flows were described by Euler's equation of motion and under certain special circumstances leading to the Bernoulli's equation. You cannot use those equations for viscous flows. We have to understand that because viscous effects were not included in those equations. So today we will be seeing that how to deal with viscous flows. But we have to understand that because of limited time that we have, we cannot elaborately derive the fundamental equation for viscous flow, which is the Navier-Stokes equation. Nevertheless, we will try to go through the salient features leading to Navier-Stokes equation. It is not strictly the derivation of Navier-Stokes equation, but some salient features that lead to Navier-Stokes equation and some of the important features of Navier-Stokes equation, and if time permits, I will work out a simple problem to illustrate that how can you solve the Navier-Stokes equation for a representative scenario. So to get into that, let us come back to that old example that you have a flat plate and fluid is coming from far stream over the flat plate. So we know that maybe far away from the plate the viscous effect is not that important. Of course, how far away it depends on the Reynolds number of flow, but at least close to the plate the viscous effects will be important. So viscous effects will be important. Let us say that we identify a control volume like this in a region where viscous effects are important and let us try to represent the forces acting on this control volume because of the viscous effects. Now forces acting on a control volume are not just due to viscous effects. We have already seen that when viscous effects are not present, there are forces acting on the control volume. What are the reasons? What are the origins behind the forces acting on a control volume if the viscous effects are still absent? One is of course the body force. Body force will be there, body force is not related to viscous effects, and normal force, normal surface force due to pressure. Remember that there can be normal component of surface force due to viscous stress. Normal component of surface force is not just due to pressure. There could be normal component of surface force due to viscous stress also. So, but that we have not considered when we were considering inviscid flow. So for inviscid flow the normal component of force is due to pressure only. Now for viscous flow you have additional normal component of force due to viscous stress and additional tangential component of force due to viscous stress. So what we will do is that we will isolate this fluid element, maybe draw it in a little bit magnified manner and try to identify forces in various directions. Let us consider a three-dimensional picture for completeness, and let us say that this is the x direction, this is the y direction, this is the z direction. For convenience in writing big equations, one may use the index notation which we will use here. So instead of x, as I mentioned earlier, we will call x1, instead of y we will call x2, instead of z we will call x3. So they are synonymous. X is x1, y is x2 and z is x3. So in general the index I, xi, I equal to 1 for x axis, I equal to 2 for y axis and I equal to 3 for z axis. Now let us give some dimensions to this control volume. Delta x delta y delta z. Okay. Now because of stresses there will be various forces, surface forces which are acting on the 6 faces of this volume. There are 6 faces of this volume. So the forces, some forces will be acting along x1 direction, some forces along x2 direction, some forces along x3 direction. So let us write only the forces along x1 direction. It will be very clumsy if we represent forces in all possible directions in a single figure. So because we are interested to write equation of motion in one particular direction, let us represent only the forces on that direction. That means that it is not a complete free body diagram, it is just representation of forces in a particular direction. So to do that, let us give some names to these faces. So A, B, C, D, maybe E, F, G, H. So we will identify the faces one by one, 6 faces, and on each of these 6 faces we will identify the forces due to stress. Okay. Remember that within the stress, pressure is already included, so we will not consider the pressure separately, we will rather split the stress into 2 parts. One part is called the hydrostatic part, which is related to the pressure. Hydrostatic means that it is like a fluid, it represents a situation when the fluid is in static equilibrium. If the fluid is in static equilibrium, then only force, normal component of force, only stress is due to normal component of stress, and that is due to pressure. So we can write that the total stress is a sum of the hydrostatic component plus a correction term due to effects which are beyond the scope of the hydrostatic component, that is which relate to the deformation of the fluid element. The component of the stress which is related to deformation, we have to understand that the hydrostatic component is not related to deformation. So the component that is related to deformation is called as deviatory component. So we have both hydrostatic and deviatory component, and when we write the total stress is a sum of the hydrostatic and deviatory component. So in this figure we will not show pressure separately. Pressure is already included within the stress in the form of hydrostatic component. So let us start with one of the faces. Let us say face CBFG. CBFG. Let us make a table. Name of the face and force along x1. CBFG. Which is CBFG? This one. We can express it better before we express the force acting on the face which is located at x equal to x, that is, so before CBFG we will be doing the other one, that is AHG. ED, the left face. The reason is that this is x plus delta x. So we will first handle with x and then we will handle the x plus delta x so that we can use the Taylor series. So AHED, what is the x component of force which is acting on it? Now x component means I have already discussed that the positive sign convention for normal component or tangential component of stress is that if its outward normal is along the negative x direction, then the force itself will be along the negative x direction. That is the positive sign convention. So let us see that how far you have remembered it. Tell what will be the indices. Tau, what is the first index? What is the direction normal? Direction normal is 1. What is the direction of action of the force? That is also 1. So tau 1 1. This is the force per unit area. So this times delta y times delta z, right? So force along x1 AHED, that is minus tau 1 1 delta y delta z. Now let us write the other phase CBFG. Now this one. So if it is tau 1 1 here, this is nothing but tau 1 1 plus del tau 1 1 del x into delta x times delta y delta z. So let us write that in this chart, tau 1 1 plus del tau 1 1 del x into delta x into delta y into delta z. Next, let us consider the bottom face. The face hatched with this green color. What is the name of this face? The name of this face is ABCD. So for this particular phase, we are interested about the force along x1 direction, either positive x1 or negative x1, but x1 direction. So force along x1 direction. Now what is the direction normal of this phase? Direction normal of this phase is minus x2, right? Therefore the positive component of this tau ij, that will take place along the negative j. So what is the name of this? Tau. What is the direction normal? Tau 2 is the first index and 1 is the second index. Very good. Then this into delta x into delta z. So we are filling up this table, minus tau 2 1 delta x delta z. Let us consider the top face. Let us consider the top face. Top face will have, in place of tau 2 1, it will be tau 2 1 plus del tau 2 1 del y into delta y I am mixing the index notation with the normal notation because you are not very conversant with the index notation. So this is like a mixture mode of writing equations. I mean, so long as you understand there is nothing wrong with it, personally I would prefer to write everything in the index notation, but because it takes time to pick it up, so I am mixing the index notation with the normal notation as much as possible. So we will first write x, y, z, and then in place of x we will write x1, in place of y we will write x2, in place of z we will write x3. That is what we will do. So in place of ABCD, then EF GH will be tau 2 1, this is the color, tau 2 1 plus del tau 2 1 del y into delta y. The other two faces, it will be very clumsy to represent in this figure, so we will just show them. There are front and the back faces, right? There are two more faces, the front face and the back face. So the front face and the back face, how can we represent this? The front face, let us first write the back face. The back face is ABGH. So let us represent the force on the back face. The back face, the outward normal is along negative z. So the back face, you have the force in this direction. I am not shading it because shading will make it very clumsy. So this is the back face. What is this? Tau 3 1. Very good. Tau 3 1 into delta x into delta y. So let us write in this table minus tau 3 1 delta x delta z and delta y, right? Delta y, and the front face, the front face is, what is the front face? EFCD. So here it will be in the other direction. Let us represent that force, this one. So in the back face it was tau 3 1, here it will be tau 3 1 plus del tau 3 1 del z into delta z into delta x into delta y. So let us write that in this table. So we have identified all the surface forces. In addition, there will be body force. I am not representing the body force, the figure is already flooded with matters, so I am not flooding that with further more matter. But we understand that, and this matter is only regarding force along x direction. So if you put force along y direction, z direction in the same figure, understand how the figure will look. So this is just the force along x direction, only surface force. So when we say force, this chart is for surface force, that we must keep in mind, not body force. So now let us make a balance of these forces. Let us write what is the resultant force surface along x direction. Resultant surface force along x direction. So we will do it very easily by considering first these two. One is minus tau 11 delta y delta z, and then plus tau 11 plus delta 11 del x into delta y into delta z. So what is the sum of these two? Sum of these two is del tau 11 del x into delta y into delta z, right? That is the sum of these two ticked forces on these two ticked faces. Then let us consider these two. These two will lead to plus del tau 21 del y into delta y into delta x into delta z. And then we consider the final one, these two, plus del tau 31 del z into delta z, delta x, delta y. Okay. Now in place of the normal notation, we can use the index notation to, in place of this will be del x1, this will be del x2, this will be del x3, right. So this becomes del tau 11 del x1 plus del tau 21 del x2 plus del tau 31 del x3 into delta x into delta y into delta z. Let us see how we can write it using the summation notation. So we can write summation of force, acting on the surface along x1 direction as summation of del tau j1 del x1, del tau j1 del x1 into delta x, delta y, delta z, where j runs from 1 to 3, xj, sorry, not x1, xj, right. So this is force along x1 direction. What about force in the xi direction? If for force along x1 direction, this index is 1. The force along xi direction, the index in place of 1 will become I, right. So summation of surface force along xi direction is summation of j is equal to 1 to 3 del tau ji del xj. This is a first observation. Now I will talk about a very common way of representing these summation conventions, that typically you do not write this summation. When you write this, actually you write del tau ji del xj, with an understanding that because the index j is repeated, there is an invisible summation acting on it. This was first introduced by Einstein and it is known as Einstein's index notation. So we will from now onwards not write the summation. How will you understand that there is summation? If there is a repeated index in the expression, you will understand that there is an invisible summation acting on the repeated index. So this is as good as writing del tau ji del xj into delta x, delta y, delta z. Okay. This is the first thing. Next, what we will do, we will write this del tau ji del xj in terms of del tau ij del xj. So, what essentially we will do, we will express tau ij in terms of tau ji or tau ji in terms of tau ij. So, how we can do that? To do that, we will appeal to conservation of angular momentum. See, when we are writing the dynamics of viscous flows, we are essentially representing conservation of linear momentum, which I have not written till now. We are just accounting for the forces. Once the accounting for the forces will complete, we will write the Newton's second law. So that is conservation of linear momentum, and that equation will give rise to the celebrated Navier-Stokes equation under certain simplified conditions. Question is, where is angular momentum conservation in fluid mechanics? The angular momentum conservation we will see will be inbuilt by relating tau ji with tau ij. So there is no separate angular momentum conservation equation that we use in fluid mechanics, but we can use tau ij equal to tau ji, which I will prove just in a moment, that you can use in the linear momentum equation. So the momentum equation that we say in fluid mechanics is a linear momentum conservation, but has the consideration of angular momentum conservation inbuilt within it. And how it is inbuilt within it, let us look into that. So to understand that, so angular momentum consideration. To understand that, let us consider a two-dimensional fluid element. That is a fluid element this is x1 direction, this is x2 direction. A two-dimensional fluid element and we will for simplicity not consider all the forces, just we will consider the forces due to the surface forces, not the body forces. I mean, if you are interested, you can take the body forces, but essentially we will find the moment with respect to an axis that passes through O and perpendicular to the plane of the figure. So if the body force, the resultant body force is passing through that, the body force will not have any moment. So what we will do is, we can of course do a very accurate rigorous analysis, but just for simplicity we will let us say that this is delta x so let us consider the normal component of force. The normal component of force is what? Tau 1 into delta y into the width of the fluid element, let us say 1. So here also, I mean, see, for if you want to be very accurate, you can write tau 1 plus delta 1 del x, let us write that, but we will see that writing of that is not necessary always. So tau 1 plus delta 1 del x into delta x into delta y into 1. I mean, we can write like this, but the thing is that these forces eventually are not giving rise to any moment. So we should not spend a lot of time in trying to represent these forces, because these forces will pass basically through O. So it will not have any moment with respect to this axis. So what forces will create moment? The tangential forces. So the tangential force, so this is what? What is the tangential force here? Tau 1 2 into delta y into 1 here tau 1 2 plus del tau for we will represent the other forces, and then I will tell you a simplified consideration just for showing the angular momentum conservation. There we will not show the gradients of the stress, that may not be that important. So let us complete the scenario here. For the bottom face, yes? No, it depends on, see here it is, here if it is tau 1 2, then the change between here to here is delta x, right? It depends on what you have assumed here. So you could assume tau 1 2 here, then it will be minus delta x by 2, it will be plus delta x by 2. Yes, that is the x direction. So if this is tau 1 1, what is the change in x from here to here? That is delta x. Okay. So it depends on what you are considering here, the change from that. Of course, I mean strictly speaking you should consider tau 1 1 here, tau 1 2 here, and here minus delta x by 2 and here plus delta x by 2. But my objective is not to show you a strict derivation. My objective is to give you the idea what leads to tau ij equal to tau ji, because we do not have that much of time to go into all the rigor. So choice of origin is up to you. Choice of origin is up to you. Okay. So this is tau 1 1, not assume that this is tau 1 1 at the origin. This is tau 1 1 at x equal to minus delta x by 2. Okay, that's all. Of course you cannot choose the origin here. So then let us proceed with this. What is this? Tau 2 1 into delta x into 1. What is this? What is this? Again tau 2 1 plus del tau 2 1 del y into delta y into delta x into 1. You can represent the body force. Let us say these are the body forces, but body forces are not that important because they are not representing any couple. There are of course some normal forces also. I will show the normal forces on this face and this face, but I will not write the expression just to save time. These normal forces, whatever are their expressions, it doesn't matter, because these normal forces do not give rise to any moment with respect to z axis passing through O. Okay. So what are the forces which give rise to moment? Let us identify that. The forces which give rise to moment are this, and this, right? Now forget about the increment in the forces. We will see that increment in the forces will give rise to only higher order terms. The increment in the forces will not give rise to the lower order term in the leading order term in the moment. The leading order term in the moment is governed by this one and this one, not the change. So what is the moment of these two forces? See, these two forces constitute a couple, right? Equal but opposite to each other. They form a couple. So what is the moment of that? Tau 1 2 into delta y into the moment term delta x. Okay? This is clockwise or anti-clockwise? This is anti-clockwise. So we call it positive moment. Then let us consider these two forces. These two forces also give rise to a moment. What is that? First of all, it's a clockwise moment. It's a clockwise moment. So minus tau 2 1 into delta x into delta y. Higher order terms will not be important as you take delta x, delta y tending to 0. So I am not writing those to keep it compact. There is no moment of the body force. So resultant moment of all forces acting is equal to, what is this? Moment of inertia with respect to the z axis passing through O times the angular acceleration. Okay. This is about z axis. IO by IO I mean a z axis passing through O. Okay. So now what is IO? So typical moment of inertia will be mass times, it will scale with mass into square of a length, right? So what is the mass? So let us write the scale of this. So what is the mass of this? Delta x into delta y into rho into 1. That is the mass of this fluid element times, let us say, delta x square plus delta y square. For a rectangular it will be this. But this, whether it is 12, 13, 1 million, it does not matter. It is the scale that is important for us. So now you take the limit as delta x, delta y tends to 0. If you take the limit as delta x tends to 0 and delta y tends to 0, first you can cancel delta x, delta y from both sides, right? This term and this term will be cancelled from both sides. If you cancel this from both sides and further take limit as delta x, delta y tends to 0, the right hand side will be 0, and this will make tau 1 2 equal to tau 2 1. Okay. So see, we have derived this equation based on two important considerations which I want to remark. The first consideration is straightforward, that we have considered the possibility of having an angular acceleration of the fluid element. So it is not necessary that for tau ij equal to tau ji to work, the fluid element has to be non-rotating or non-accelerating. It may be rotating but non-accelerating. Even if it is accelerating, the acceleration term goes away because of the higher order terms. This is the first thing. But this is not that subtle. The second important consideration is that when we are writing this force, we are not writing any body couple. There may be a couple which is acting on the volume of the fluid element, that is called as body couple. Usually fluids will not sustain body couples, but there are special types of fluids which will sustain body couples. These types of fluids have particulate matters inbuilt within the fluid, so particles embedded within the fluid. A classical example may be blood. Like blood has the blood cells. These blood cells are like particulate matters which can sustain body couple. These types of fluids are called as micropolar fluids. So micropolar fluids can sustain body couple, but that body couple we have not represented here. So if we have body couple, then tau 21 equal to tau 12 would have not worked. There will be an additional term due to the body couple. So we have to understand that this derivation is based on an assumption that there is no body couple. Okay. So we can generalize. So what is our inference? That we can generalize from here that tau ij is equal to tau ji. Therefore, coming back to our previous expression for force, this expression, in place of del tau ji del xj, we can write del tau ij del xj. Okay. So we have identified the surface forces. Now let us write the equation of motion. Of motion along xi. What is equation of motion along xi? Resultant force along I is equal to mass times acceleration along I for the fluid element. What is the resultant force along I? Resultant force is summation of surface force along I and summation of body force along I. So the surface force this is the surface force. What is the body force? Let us say that Bi is the body force along I per unit volume. So this is body force per unit volume. Body force along I per unit volume. The volume of the fluid element is delta x, delta y, delta z. Let us now write the right hand side. What is the mass? Rho into delta x into delta y into delta z. And what is acceleration along I? So in short notation dui dt, but let us write it in more expanded form. Del ui del t plus what are the three terms like? Let us imagine that term in the standard notation and then we will write in the index notation. U del u del x plus v del u del y plus w del u del z. So u1 del ui del x 1 plus u2 del ui del x2 plus u3 del ui del x3. Okay. The same thing that you have learned just expressed in index notation. So now you tell me these three terms compacted together, how can we write? Uj del ui del xj, right? With an invisible summation over j equal to 1, 2, 3. So if you now collect the terms in the right hand side and in the left hand side and take the limit as delta x, delta y, delta z tending to 0, the higher order terms will get nullified and delta x, delta y, delta z will get cancelled. And just for the sake of writing, we write the right hand side in the left and left hand side in the right. That is the standard way of writing in fluid mechanics. So rho del ui del t plus uj del ui del xj is equal to del tau ij del xj plus bi. This equation is known as Navier's equation. Now let us say that what we will do with this equation. Our ultimate objective is to solve for the velocity field. How many components of this equation are there? I, how many? I equal to 1 will be one component, I equal to 2 will be another component, I equal to 3 will be another component. So we have these three equations plus we have the continuity equation which always has to be satisfied. So in terms of fluid flow, how many equations are there? 3 components of this equation plus the continuity equation. So 4 equations. How many unknowns are there? So let us identify the unknowns. In general, rho may be an unknown, rho may be known also, but rho also may be unknown. So rho, u1, u2, u3 and tau ij, how many unknowns are there? I could be from 1 to 3, j could be from 1 to 3. So total 9 are there, but because tau ij equal to tau ji already that is known, so you have 6 unknowns. So total 6. That means 1, 2, 3, 4 plus 6, 10 unknowns, and you have only 4 independent equations. So that doesn't close your system of equations, and you require closure models to close your number of equations with number of unknowns. To address that, you require special consideration about the nature of the fluid, which is known as constitutive behavior of the fluid. Constitutive behavior is the constitution of the fluid. Like all of us have certain constitution, right? Maybe you take 1 kg of mutton and still in the next morning you are very fine. If I take 1 kg of mutton, next morning possibly that will be my last morning in my life. So every person have every people have some typical constitutive behavior in which they can respond to a disturbance. Similarly, fluids can have certain particular behavior by which they can respond to an input. So that response to an input is in terms of stress strain behavior. Now for fluid, it is not important to relate stress with strain. Rather, it is important to relate stress with rate of strain or rate of deformation. This was emphasized very emphatically in our introductory lecture by Professor Som, that you require for fluids stress to be related to rate of deformation. So our objective will be to relate tau ij with the rate of deformation. I will not go into the derivation of how we are going to do that, but I will give you some particular consideration. So tau ij will have 2 parts. One part will be related to deformation, another part will be not related to deformation. So as we have already discussed, you have tau ij as the hydrostatic part, plus you have the deviatory component. The hydrostatic part is not related to deformation and the deviatory part is related to deformation. So hydrostatic part, it has been covered by Professor Ghosh-Moulik, that you have this one with delta ij is equal to if j is not equal to I. This is known as Kronecker delta. It has been elaborated by Professor Ghosh-Moulik. Now you consider the deviatory component. The deviatory component is a function of deformation of the fluid. What kinds of deformation the fluid have on a gross? See, the fluid has volumetric translation, but the translation culminates in the form of volumetric deformation and angular deformation. Angular deformation is shear deformation plus the fluid has rotation. Now the stress, deviatoric stress, which is related to deformation of the fluid, out of these three, there will be one particular component which will not give rise to any stress. I am telling you three components. One is volumetric deformation, another is shear deformation, another is rotation. Out of these three, one will not give rise to any stress. What is that? Rotation. Because rotation sort of gives like to a rigid body type of motion effect that doesn't give rise to any deformation. So deformation is attributed to angular deformation as well as volumetric deformation. So I am just writing it qualitatively. So due to angular deformation or shear deformation plus due to volumetric deformation. Now this, see, this is a parameter which is like a force, and these are parameters which are kinematic parameters. So you can relate a force with an effect and force with a kinematic parameter, and it requires constants. Like for example, for elastic solids, for stress will change. Elastic solids, and that property will require a constant. Now, a general fluid, you would have required to describe this relationship between deviatoric stress and these rates of deformation, you would have required 81 number of material constants, 81 constants. But the issue is that we know that we deal with air, water, these kinds of fluids, we do not require 81 constants to describe these fluids. In practice we never required that. So how we can manage with this is that we consider special cases of homogeneous fluid and isotropic fluid. We consider special cases of homogeneous fluid and isotropic fluid. So when we consider special cases of homogeneous fluid and isotropic fluid, what do we mean by this? Homogeneous means independent of position. That at whatever is the fluid property at a given location, the same is the fluid property at a different location. It is homogeneous. Isotropic means it is direction independent. That means if you have a set of coordinate axes to represent your situation, if you now reorient your coordinate axis by say rotation, translation, reflection, you make these considerations, it can be shown that instead of these 81 constants, you can deal with 2 constants. But remember that the consideration of this 81 constant doesn't follow for any general fluid to begin with. It is valid only for Newtonian fluid. So for fluids, for the Newtonian fluid, the stress is linearly mapped with the rate of deformation. Linearly mapped. The stress is linearly mapped with the rate of deformation. So if you have the stress linearly mapped with the rate of deformation, then that linear mapping or that linear transformation gives rise to 81 constants, which can be transformed into just 2 constants for homogeneous and isotropic fluid. So what are the special considerations that we have made? These 81 constants for Newtonian fluid. So for two constants for homogeneous plus isotropic plus Newtonian fluid. So the Newton's law of viscosity, if somebody asks you that what is Newton's law of viscosity, the Newton's law of viscosity in a qualitative term is not tau equal to mu du dy. There are many ways of representing a theory. See, if you give me a task of explaining Ramayana and Mahabharata to my 3-year-old son, I will not go into what is the real mythological thing and to explain it. There are books, Ramayana for children, Mahabharata for children, like that. Similarly, there are considerations like fluid mechanics for children. That means you start with young people to describe that what are the things. So then you say tau equal to mu du dy. But it is incomplete because it is under a very special condition that tau equal to mu du dy. But the general is the stress is linearly mapped with the rate of deformation, and if that linear mapping is possible, then it's a Newtonian fluid. Okay. So Newtonian fluid plus isotropic fluid plus homogeneous fluid will give rise to two constants. These two constants, let us call one constant as lambda, another constant as mu. Why these lambda and mu are different? Because we have two types of deformation. One is volumetric deformation, another is angular deformation. So one constant must be related to angular deformation and one constant must be related to volumetric deformation. Let us say that this lambda is related to volumetric deformation. So tau I is due to volumetric deformation. This is lambda into the rate of volumetric deformation, volumetric strain. It was derived by Professor Shom that the rate of volumetric strain is nothing but divergence of the velocity vector. So lambda into divergence of the velocity vector. And mu will give rise to tau I deviatoric due to shear deformation. So it is mu shear deformation del ui del xj plus del uj del xi. Okay. So you can maybe you follow this term, but I will just give you an example. Right? This is nothing but like V is U2 and U and X1 is X. So del V del X plus del U del Y. This is like del V del X. So cross terms. So this is the rate of deformation expressed in an index notation. Water, air, these are, I mean, the common fluids with which we deal. Actually anisotropic fluids are not very common which we deal with in engineering. In engineering, the kinds of fluids that we deal with are homogeneous and isotropic. So this is like very practical consideration. The next consideration is that it can be shown, I will not go into again the derivation, that it can be shown that there is a relationship between lambda and mu. Now can you tell that I don't care about lambda? When do I not care about lambda? I will not care about lambda when the term which is there associated with lambda is 0. That means divergence of velocity vector is 0. So I will not care with lambda when it's incompressible flow. So I do not mind what is the value of lambda because lambda into divergence of velocity will be 0 if divergence of velocity is 0. So for incompressible flow we don't care about lambda. For compressible flow there will be a relationship between lambda and mu, and that relationship was postulated by Stokes. This is known as Stokes hypothesis. So the first point to consider is that this Stokes hypothesis, first of all, it's a hypothesis, there is no proof, just like Avogadro's hypothesis. You do not have a proof, but there are physical intuitive arguments. I will go into that intuitive argument to discuss that when it is valid. But the first thing is that we don't care about Stokes hypothesis at all for incompressible flow, because for incompressible flow the term lambda doesn't matter, the volumetric strain term doesn't matter. But for a compressible flow we discuss about two important concepts. One concept is called as mechanical pressure and the other is called as thermodynamic pressure. Mechanical pressure relates to the normal component, average normal component of the stress. So mechanical pressure is defined as tau 11 plus tau 22 plus tau 33. These are the normal component of stress, average of that, with a minus sign because positive sign convention is tensile stress and pressure by definition is compressive. So that is mechanical pressure. So it's purely a mechanical concept. This is what we measure when we measure by a pressure measuring device. Essentially the average normal component of force. That is what we measure when we measure. Thermodynamic pressure is a pressure that is defined by the equation of state. Equation of state of that is for an ideal gas, for example, PV equal to RT. So equation of state. So you have a mechanical pressure and you have a thermodynamic pressure, and this mechanical and thermodynamic pressure, they are in general different, because a molecule will have different degrees of freedom, translational degree of freedom, rotational degree of freedom, vibrational degree of freedom, and there is a time that is necessary that all are converted into a translational degree of freedom that is manifested in the form of mechanical pressure, which is the normal component of stress. This interconversion of degrees of freedom takes time. Now the question is that what time you are allowing a fluid. Let us say there is a bubble which is expanding and compressing very fast. If the bubble is expanding and contracting very fast, then what is happening? You are not allowing it to adjust to the disturbance. That means it is not coming in local equilibrium. If it is not coming in local equilibrium, then mechanical pressure and thermodynamic pressure, this equality cannot be achieved. But if it is a relatively slow process, then that can be achieved. Question is what is slow? Every fluid has a relaxation time. That means if you give a disturbance, it will have some time to adjust to the disturbance. If you kick one of your enemies, now the enemy will take some time to adjust to the kick before giving you a reply kick, right? But if you are continuously kicking with a very high frequency, many times in Hindi movies we see that the villain is kicking somebody continuously. So the other person, poor fellow, is lying on the floor and not able to adjust the disturbance and not able to resist. If that is not possible, then mechanical pressure and thermodynamic pressure equivalence cannot be achieved. If that can be achieved, then we say that the Stokes hypothesis is valid. But fortunately, fluids are remarkable materials. Typically, most of the fluids have very quick relaxation. That means the relaxation time is very, very short. It is so short that no matter whatever is the time scale of disturbance that we impose on that, it will quickly adjust to that. So that for most of the fluids that we encounter in, for most of the situations that we encounter in practice, Stokes hypothesis is valid. So that makes it a remarkable hypothesis. It cannot be directly proved, but the practical situation of time scales demand that the mechanical pressure and thermodynamic pressure, they are equivalent, so that we can write this. Now for this particular coordinators workshop program, we will not bother so much about lambda, because the physical situation that we will be covering will be consistent with incompressible flow. So because it will be consistent with incompressible flow, I have already mentioned matter for incompressible incompressible flow because this term will be 0. Anyway, let me write the expression for tau ij and then we will proceed with the consideration that incompressible flow minus p delta ij plus lambda divergence of velocity. Again, I use notation vector and x together plus mu del ui del xj plus del uj del xi. Now tell me what are the assumptions under which this is valid? Yes? Newtonian fluid, homogeneous fluid, isotropic fluid, right? Now if I write lambda is minus 2/3 mu, that Stokes hypothesis is valid. That is called as Stokesian fluid, a fluid which obeys Stokes hypothesis. So now see, there is another interesting thing. There is a lot of physics associated with term that you have a minus, positive, negative, right? That means physically for a fluid element which is already stretching, the incremental stress required to stretch it further is negative. That is, you require less stress to stretch it further if it is already stretching. That's why this negative term appears. Now we will, let us write the assumptions. Homogeneous, isotropic, Newtonian, Stokesian. Next, a very important additional assumption that it is incompressible flow. If you have incompressible flow, then you have the divergence of velocity equal to 0. So tau ij is equal to minus p delta ij plus mu. So incompressible flow in addition to the previous assumptions, plus previous assumptions plus incompressible flow. But again, as I told, that if it is incompressible flow, whether it is Stokesian or not, it really doesn't matter because the term anyway will be 0. Okay. Now we have been able to express tau ij in terms of the velocity gradients and pressure. So let us substitute this equation in the Navier's equation. Let us recall the Navier's equation. So in the Navier's equation we will substitute the expression for tau ij. So rho del ui del t. So let us write, substitute in Navier's equation. It is very straightforward. This tau ij we have substituted in terms of this equation. Okay. So let us simplify the right hand side. Let us simplify the right hand side. Delta ij is 0 in general except when j equal to I. When j equal to I, this will become minus del P del xi and then delta ij equal to 1. So the first term is minus del P del xi. Next term del del xj of mu del ui del xj. Next term del del xj of mu del uj del xi. And the last term is bi. Now let us concentrate on this term. Del xj of mu del uj del xi. If the partial derivative second order is continuous, then we can swap these two. We can either see if you have a second order cross partial derivative continuous, we can either differentiate with respect to x first or y first. Similarly, here we can swap these two and we can write del del xi of mu del ui del xj. Mu del uj del xj. What is del uj del xj? Del uj del xj is nothing but del u1 del x1 plus del u2 del x2 plus del u3 del x3. This is like del u del x del v del y plus del w del z. This is the divergence of the velocity vector, which is 0 for incompressible flow. We have considered the special case for incompressible flow. So this is 0 for incompressible flow. So we have come to the final form of the equation. Rho del ui del t plus uj del ui del j is equal to minus del p del xi plus del del xj of mu del ui del xj plus bi. This is not the general Navier-Stokes equation because we have considered the special case of incompressible flow, which is there in the purview of the problems that we will be solving for the purpose of the tutorials that we will organize after this. So if it is a compressible flow, there will be an additional term with lambda. Just there is a term with mu, there will be an additional term with lambda. In Stokes hypothesis, we can substitute there lambda is equal to minus 2/3 mu. Remember, this is not the general form of the Navier-Stokes equation. So this is called the Navier-Stokes equation for incompressible flow. For Navier-Stokes equation for general form for compressibility effect, one additional term will be there. We are not going through that. So to summarize, what we can say, let us now see how many equations and how many unknowns we are having. So how many equations and how many unknowns we are having? So this has three components. How many of these components are there? I equal to 1 will be the x component, I equal to 2 will be the y component, and I equal to 3 will be the z component. So three components. Plus you have the continuity equation. So you have four independent equations. How many unknowns are there? So you have U1, U2, U3, pressure. What about rho? So rho need not be constant. Like for example, it could be a function of temperature, which is commonly there in natural convection. Okay. So if rho is a function of temperature, you require to solve for the temperature field. And for that, you have to bring in what? You have to bring in the energy equation, which falls in the purview of convective heat transfer. So there may be additional equations necessary. If rho is a function of pressure and temperature both, you require an equation of state to describe rho as a function of pressure and temperature. So additional equations may be necessary to describe additional effects. For the purview of this course, let us assume that we do not have those complications, that let us say rho is a constant, just for simplicity. If rho is a constant, you have four equations and you have these four equations. So that closes the unknowns with the equations. I will conclude by describing two important interesting features of the Navier-Stokes equation. What are the two important and there are many interesting features, of course. First of all, see this Navier-Stokes equation, you can see from here that these equations are non-linear. So these are coupled non-linear partial differential equations. These are coupled non-linear partial differential equations. The non-linearity arises because of which? Because of these terms, like u del u del x, v del u del y, w del u del z. These terms give rise to the non-linearity in the Navier-Stokes equation. So non-linear partial differential equations are very difficult to solve analytically. This is the first important consideration. So solution of Navier-Stokes equation is a challenging job. I am just giving you a prelude to CFD. Why we emphasize so much on CFD or numerical computation of the Navier-Stokes equation. So that is the first challenge. The second challenge is that you have a pressure. You have a pressure, but there is no separate governing equation for pressure. This is a governing equation for velocity. So try to appreciate this thing. You have a variable called as pressure, but you do not have an explicit governing equation that describes pressure. Governing equation for pressure. This momentum equation is governing equation for velocity, but not directly governing equation for pressure. So this is the challenge. How can you overcome the challenge? There are two ways of doing it. One way is, like I give you a simple analogy. Let us say you have a headache. So if you have a headache, there are two options. One option is you take medicine or you go to a doctor to get relief from headache. There is another more drastic option. You cut your head. If you cut your head, there is no head, so there is no question of headache. If you have headache, why do you have head? All of us have tensions in life because we can understand stress and strain in life. If we do not understand stress and strain in life, we have no head. So the thing is, eliminate pressure. If you eliminate pressure, you can come up with variables which do not explicitly contain pressure. An approach which is, of course, valid for restricted class of problems, that is stream function vorticity approach. And the other approach is that you consider pressure and link this pressure with a continuity equation. Using the continuity equation, you artificially derive a governing equation for pressure, because these three equations are for velocity. Continuity equation is for conservation of mass, but you can link this with the pressure, and that gives additional equations. This is called as primitive variable approach. And then using that additional equation, you have governing equations for velocity and governing equations for pressure. You can solve that, and that is one of the ways in which modern CFD solves the Navier-Stokes equation numerically. So I will try to conclude here because we have covered enough material for one lecture, and what I just want to say is that we will be working out some special type of problems for which exact solutions of the Navier-Stokes equation exist, and we will work out that problem. I will myself work out that problem, one special type of problem, in the tutorial session for this Navier-Stokes equation chapter. Thank you very much.